Hello, welcome to my channel CNCR Science and Math Concept. Here we are doing the question from class 12 physics, topic dual nature of matter and radiation. The question says the work function of cesium is 2.14 electron volt. Find the threshold frequency for cesium and the wavelength of the incident light of if the photocurrent is brought to zero by stopping potential 0.60 electron volt. So the first of all, we are given work function is equals to 2.14 electron volt. Now what do you mean by work function? Work function is the minimum energy that is required to just eject the electron from the surface of metal without imparting any kinetic energy to the electron. So this is the work function. This is in electron volt. If you want to convert it into joule, then 2.14 into 1.6 into 10 to the power minus 19 joule. This is the work function. Now in part A, we have to find out threshold frequency. Threshold frequency. What do you mean by threshold frequency? The threshold frequency is the minimum frequency which is required, or the frequency at the point which is required to eject the electron is called threshold frequency, and it is denoted by nu 0. It means here we can say that energy provided by threshold frequency h nu 0 will be equals to work function, because threshold frequency is the minimum frequency required to eject the electron and work function is the minimum energy required to eject the electron. Therefore, h nu 0 is equals to work function, or then threshold frequency will be equals to work function upon Planck's constant. Now there is only the numerical part left for this. Value of work function is 2.14 into 1.6 into 10 to the power minus 19 joule divided by Planck's constant is 6.63 into 10 to the power minus 34 joule second. On solving this, we get the threshold frequency is equals to 5.16 into 10 to the power 14 Hertz. So this way we have calculated the threshold frequency for part 1 of the question. Now we will do the part B of the question. In part B of the question, we have to find the wavelength. We have to calculate wavelength for which the photoelectric current is brought to zero by a stopping potential of 0.60 electron volt. Now what do you mean by stopping potential? Stopping potential means the potential required so that the electrons are stopped. And when the electrons are stopped, the current in the circuit will become zero. In that case, we can say that maximum kinetic energy is equals to stopping potential energy. So maximum kinetic energy is given by kinetic energy provided minus work function, which is equals to EV0, that is potential energy provided by the stopping potential. Now kinetic energy that is provided is given by hc by lambda minus work function is equals to EV0. Now we put the values, or first we solve the formula. hc by lambda is equals to EV0 plus work function. Therefore, lambda is equals to hc upon EV0 plus work function. Now we put the values and then we find out what will be the wavelength. So now we put the value. The Planck's constant is 6.63 into 10 to the power minus 34. Speed of light is 3 into 10 the power 8 whole divided by, now EV0, stopping potential is given 0.60 electron volt. I have not put the value of E, and work function is 2.14 electron volt. So now this total will become, now I multiply 6.63 by 3, that is 19.89 into 10 the power minus 26 divide by, now 2.14 plus 0.6 is 2.74 electron volt. So I've now put the value of E, that is 1.6 into 10 the power minus 19. On solving this is coming out 453.7 into 10 the power minus 9. Therefore, wavelength comes out to be 453.7 nanometer. So this way we have done the calculation for calculating the wavelength of incident light, so that at given stopping potential the photoelectric current becomes 0. That is all for this question. Keep watching my other videos for more challenging questions, and do